Okay. Hi. I hope it wasn't too miserable when you lost an hour this weekend. Okay. So let's continue talking about graphs. So the first half of today, I'm going to switch gears a little bit. And instead of talking about, last time we were kind of philosophical. I drew pictures of graphs for you. And we talked about depth first paths. And we drew a picture of it. And it was great. But one question you might have is, how do you actually implement this thing? So sure, we saw depth first paths. It was really nice on the slide, and we had the picture, and we were coloring the nodes white to mark them. But how would you actually implement something like this in code? So we need to figure out today, how would you write this in code? In particular, we need to figure out what is the API for a graph. API stands for these words. I never remember what they are. But basically, the idea is, what services or what methods are we going to give to the users of our graph? So we're going to build the graph class, but like what methods does the graph user get to use? So for example, when we built a list, we gave the user the ability to add first, and we gave the user the ability to add last. And you and your projects gave the user the ability to add in the middle of the list. So which of these, or did you do that in project one? I don't know. But that's a decision you have to make. Do you allow the user to add in the middle of the list? Do you not? And so we're going to have to make those decisions for the graph. What methods do we give to our users? And the methods that we give will determine how people who use our graph need to think about the graph, because they only have access to the methods that we define. So we're providing a certain set of services. You can use these services, and that's it. And the client programmers have to use those services to interact with their graph. And then after we figure out what we give to our users, the interface, then we have to figure out what's the actual implementation. So what data structures do we actually use as programmers to write the graph class and to give the users the methods that we decided we wanted to give them? And the key idea, if you don't get anything else today, the key idea is your decisions for what methods you give to the user and how you implement the graph, they have huge implications on how fast the graph runs. So runtime, how much space the graph takes up, and how easy it is to write and use the graph in code. So we're going to make these decisions, and depending on if we make good decisions or bad decisions, we can have huge impacts on how fast the code runs and how easy it is to write code. So hopefully, we make some good decisions. OK, so at this point, you could implement the graph class in so many different ways. I will show you just one of many different ways you could implement it. This one is inspired by the optional Princeton textbook, which you might have seen before. So I'm going to make a decision, which you don't have to make in your project, but I'm going to decide that instead of allowing you to create nodes with any sort of label in them, I'm going to force you to only have integers as labels. So I'm going to say you can't have a node called Dallas, but you can have nodes called 0, 1, and 2. That's my decision. If you don't like it, you can build nodes with Dallas. It's OK. But that's my decision. So the question then is, if I'm only forcing you to have integers in your graph, how could you represent a graph like the one on the left with Dallas, Austin, and Houston? Well, one thing you could do then is you could first build the graph with numbers, 0, 1, and 2, and then keep track of a map. That maps Austin is represented by 0, and Dallas is represented by 1, and Houston is represented by 2. So in effect, this structure on the right is the same as the structure on the left, but I'm forcing you to build it like this because I am restricting you to only having integers. And this is just going to make thinking about the graph a little bit simpler for us, but maybe the users of the graph now have to think about this map. Do you like that? Do you not like that? It's your decision. OK, so that's my first choice. If you like it, you can use it. If you don't have to. But I'm going to force all vertices to be integers inspired by the Princeton textbook. OK. And remember, if you don't want to represent numbers and you want to represent strings or whatever else, you can keep track of a map that maps the numbers to the strings, or vice versa. OK, great. So again, inspired by the Princeton textbook, these are the features that we're going to give to our users. So these are the services that we're providing to our users. They can interact with the graph in these ways and no other ways. And if you want to let the user interact in other ways, you can, but the Princeton textbook doesn't. So the Princeton textbook says, if you would like to create a graph, you must tell me in advance how many vertices are in the graph. So you decide ahead of time, I want a graph with 10 vertices. You want more? Too bad, you get 10. That's what the Princeton algorithms textbook says. If you don't like it, you can add vertices yourself. But the Princeton's textbook says you decide ahead of time, I want 10 vertices. That's all you get, no more. However, you can add edges all you want. So the Princeton's textbook says, let's add a method called addEdge, which creates an edge between any two vertices. Notice how we're passing in integers. Why is that okay? Because we enforced earlier that all the nodes in the graph are labeled with integers. That's why these arguments are ints. And then the only way in which you can interact with the graph and ask it questions is you can say, hey, vertex number 5, what are all the vertices adjacent to vertex number 5? That is, all the vertices connected to 5 by a single edge. And this is going to return an iterable. I actually don't know why they chose to do that. You could also return a list here if you wanted to. But the key idea is it's going to return a list or an iterable or a collection of all the vertices represented by numbers that are adjacent to the vertex that you passed in. And then you can also ask how many vertices are in the graph in total. You can also ask how many edges in the graph in total. And that's it. That's all the Princeton's algorithms textbook graph class lets you use. So if you choose to use this implementation of a graph, these are the only services that are provided to the user of the graph. They want to do something else, they have to do it themselves. We don't give it to them. We let you add edges and ask for adjacent edges, and that's it. Okay. So here's an example. Let's say I'm building a graph, and I'm really intensely curious about the degree of vertex 1. So I really want to know how many edges are coming out of vertex 1. In the picture, I can see it's 2. There are 2 edges coming out of vertex 1. But if I were to implement the graph using this class, how would I ask this graph in code how many edges are coming out of vertex 1? I look through the methods, the services that are provided to me, and look, there's no degree method. So I look here, there's no way for me to ask the graph how many edges are coming out of vertex 1. It's like going to a store and you're like, can you gift wrap this for me? And the store says, no, I don't provide the service. You have to gift wrap the thing yourself or whatever. So in this case, because the graph does not provide the service of telling me how many edges are adjacent to 1, I have to do it myself. So here, the person using the graph has to write their own method where they've taken a graph, taken a vertex, and then they have to write their own code, which somehow like iterates through the adjacency and like counts the number of vertices that are adjacent and returns the count. And this is how the user of the graph would figure out that the vertex 1 has 2 edges coming out. They have to write this code themselves. If you don't like this, if you find this distasteful, when you're writing your own graph class in project 2, you could add your own method called degree. And this way, the users of your graph could just call the degree method to see how many edges are coming out of a vertex. So it's kind of a decision that you get to make. Do you want the users to have to do this? Or do you want to provide this as a service to your users? That's your call. But this is what the Princeton's library decided. OK. Stop for questions, thoughts? OK. Great. So something else you might want to do is maybe you want to print the graph. And you can print it in all sorts of different ways. I'm just going to print it in this lazy way where I write out all the edges. And so question for you is, could you print the graph by just asking the graph to print itself? I look through the methods. No, there's no service for printing the graph. I look, these are the only things that the graph lets me do. There is no print method. So if I were someone using this graph and I wanted to print out the graph, I would have to write it myself. So you can try and think about how you'd write this. I'm trying to picture it. And remember, the only things you can use are these methods here and nothing else. So somehow I'm probably going to have to use the adjacent method and be like, well, what are all the vertices adjacent to 0? Print those out. What are all the vertices adjacent to 1? Print those out. What are all the vertices adjacent to 2? Print those out. So maybe something like this. You don't have to start out the code too hard. But the idea is I iterate through all the vertices. For every vertex, I look for all its adjacent vertices, and I print it. And again, this is the user doing this, because the graph class did not provide this service. So you go to the store, you're like, can you do this for me? And the store is like, no, you got to do it yourself. You know, like it's like going to IKEA. You have to go home and like put the couch together yourself. So that's what I got to do here. And if you don't like it, you can add a print method yourself. But they didn't. Okay, so here it is, my favorite picture again. And again, it's showing you that, here's the monk in the back, and it's providing you with the show, the puppet show, with these methods, the graph constructor, add edge, adjacent, and that's the only thing you get in the show. And everything else you want to do, you have to manipulate the puppets yourself to make that happen using the methods that we provided. So that was our first choice, which is what services do you want to give to the users of your graph class? And that's what we chose. But again, you can choose something different. And depending on what you choose, the implementation of all these different services or methods like print or depth-first paths, they could be simple, they could be fast, they could be slow, and it really depends on what you give to your users. So that was our first question answered, which is what services or methods do we give to our users? But there's a second question, which is, well, how do you actually build the graph in memory? So we talked about these are the services that we give to our users, but what data structure do we use to actually implement all these methods that we've been talking about? So that's something we're going to have to think about next as well. So I guess before we get to that, one other thing we should think about is, how do you represent this depth-first paths thing? So the idea that the Princeton algorithms library uses, but you don't have to use, is they decide, I'm actually going to build a new separate class that represents depth-first paths. So if you think of classes or objects as representing things in the real world, I have an object representing a graph. I have an object representing a dog. You could think of this object is like this wise bodhisattva, and it's like this really wise creature that knows all about a graph. So one thing you could do is you could create a constructor, and you pass in a graph and pass in a starting vertex, and you give this to the bodhisattva, and she thinks really hard about the graph. She learns all of its truths, and then after the constructor runs, now you can ask her questions. You can ask her a question like, hey, is there a path from S to V? And she'll say yes or no. You can also ask her a question like, hey, what is the path from S to V? And if there is one, then she'll return it to you, maybe in the form of an iterable or a list. So you could do this. Some people like doing this. If you ask our TAs, a lot of people didn't do this, and they just built the graph or the depth-first paths into their graph class. So it's a design choice that you get to make, but this is what the Princeton implementers chose to do. They built a paths class representing this wise sage who knows all about graphs. You give the sage a graph. The sage thinks about the graph really hard, and then you can ask her questions about the graph. So I find that kind of neat, but it's your choice. OK, so example usage, you give her a graph, G. You say S is the starting vertex at 0, and then you can ask her questions, and she'll answer your questions. Kind of cool. OK, so I guess we could review depth-first paths if you want to. Does anyone really want to see it again? Anyone not want to see it again? It's just go on. OK, mixed opinions. I don't know if Zoom has opinions. OK, I'll quickly speedrun depth-first paths. And if you want to go faster or slower, just tell me. OK, so remember, depth-first paths, this was the final algorithm we saw last time. And the key ideas were you should keep track of every vertex. And you should mark a vertex when you visit it, because I don't want to visit a vertex twice. I don't care about a vertex's opinions twice. So every time I visit a vertex, I'm going to mark it so I avoid visiting it a second time. I don't want to be trapped in that infinite loop where I visit the same 2 vertices over and over again. That's stupid. So every time I visit a vertex, I'm going to mark it and then never visit it again. So look, I go to 0, I mark it. It's white. I will never visit it again. And then for every neighbor of V, so in this case, just one neighbor and it's 1, I will write how I get to that neighbor, and then I will call DFS on that neighbor. So how do I get to 1? I get to 1 using 0. OK, so I wrote it down. I kept track of how I got to 1. And now I can go call DFS on 1 with a reminder to myself that when I'm done with 1, I got to go back to DFS of 0 and finish up whatever I was doing there. So here I am in 1. I look for all of its unmarked neighbors. 0, it's marked already. I don't want to go backwards. But 4 is not marked, and 2 is not marked. So I'm going to need to mark both of these and call DFS on them. I will start with 2. And later, if I have to, I'll come back and do 4. So I will write how I get to 2. Look, how did I get to 2? I got there from 1. So I wrote it down. I called DFS on 2. I left a reminder to myself that when I'm done with DFS of 2, I got to go back and finish DFS of 1. So here I am at 2, and the process continues. So I look for the unmarked neighbors. It's just 5, so I go there. Reminder to myself, go back and finish DFS of 2 when I'm done. Every time I visit someone new, I write down how I get there. So here I am at 5. I go to 4. I go to 3. And it looks like I'm at a dead end. There's no more neighbors. So 3 is going to return. But remember, when 3 returns, I still have to call DFS of 4. I didn't finish that. So DFS of 4, that's also done. DFS of 5, that's not done yet. So 5, it had to check 4. And then once it's done checking 4, now it's going to check 6 and 7. Those are going to return. And then 5 still has to check 8. So I check 8, writing down the edge 2's all along the way. And now everything is marked. So I return, return, return. Everyone's done. And so that was depth first paths, speedrun. OK. By the way, one thing that I didn't mention last time, but I actually wrote down for you, is every time I called DFS for the first time, that is, I marked the vertex, I called DFS on it, I actually wrote down the order in which I called DFS. I also wrote down the order in which the DFS calls finished. So for example, if I go all the way back, look, I called DFS on 0 first, then I called it on 1, then I called it on 2. So I'm writing down the order in which I'm calling DFS up here. And all of these were kind of half done. The first DFS that truly finishes is DFS of 3. So when it finishes, I write it down here. And now DFS of 4 is totally done, right? All of its neighbors are marked, and I've called DFS on them. So I can return from 4. Here I am at 5. I have not returned from 5 yet, because there's still more stuff to do. So I go to 6. I go to 7. Now 7 is done. Now 6 is done. Here I'm at 5. But 5 is not done yet. There's still more to do. So I go to 8. And only now is 5 done, and then 2 is done. So I wrote down the order in which DFS finished, which is kind of cool. So I guess this would be a good time to finish this last little section that I forgot to do last time. So do you remember last time? Sorry for the digression, but do you remember last time we talked about tree traversals? And we said there are many different ways to iterate through the nodes of a tree. Well, it turns out there are also many ways to iterate through a graph. And in fact, those orders that we just saw, those were ways in which we could naturally order an iteration through all the vertices. So one possible way to order a iteration through all the graph's vertices is called DFS preorder. Why is it called preorder? Because you did the thing, whatever action you care about, before calling DFS on its neighbors. So if you go back and look at the code, what do? We first set the edge to, and then we called DFS. So this was a DFS preorder traversal. So we did a thing, which was we marked edge 2, and then we called DFS on all of its neighbors, and that gave us this order. So that's one particular order in which you could traverse this graph. This is the order in which we call DFS. And if we are doing something before calling DFS, then this is the order in which the nodes get visited. But there are other orders like DFS post order. This is the order in which the DFS calls return. So that's the second order we saw from earlier. And this would be the order in which, for example, like 3 was the one that finished first, and then 4 finished, and then 7 finished next. So if you were to do something after calling each DFS call, so for example, maybe you did something like this, where you decide, I want to print every single node after visiting it, and after calling DFS on all of its neighbors, this would be the post order, and the result would be this order that we saw from earlier. So all of this is to say, remember, in order, post order from trees, there's something pretty similar for graphs. And again, it just depends on, do you perform the action before calling DFS on the neighbors, or do you perform the action after calling DFS on its neighbors? And if you perform things before calling DFS on its neighbors, you get this, the order in which DFS is called. If you perform things after the DFS call to all of its neighbors, you get this order, which is equivalent to the order in which the DFS calls return. So this is the graph version of tree traversals. OK, and this order, we will see it today, so I won't talk about it yet. But stay tuned. OK, traversals, OK. All right, see, I finished the thing from last time. OK, great. So again, here is DFS, but in code. I will not talk about it in gory detail, but you can read it if you would like. But the key idea is, if you look at how we implemented this, we only use the graph methods that the graph implementers over at Princeton gave to us. They told us you can call dot adjacent, and that's kind of about it. So that's the only thing we use to interact with the graph, is we call the adjacent method. Everything else we had to implement ourselves as the depth first paths Bodhisattva. Okay, great. So that's one possible way you could implement DFS. You mark the vertex, you go through all the adjacent vertices, you write down how to get to those adjacent vertices using the edge2 array, and then you call DFS on all of the neighbors. Okay, great. Again, I will not read this in detail, but this is how you might write path to or has path to. So how do you check if there's a path to a vertex? You can check if it's marked. If it's marked, it means we found a path to that vertex. And how would you actually find the path to the vertex? You might write some code like this. I will not talk about it, but it's something we kind of saw last time. So remember, like, how do you get to 8? You get there from 5. And how do you get to 5? You get there from 2. And how do you get to 2? You get there from 1. And how do you get to 1? You get there from the source. So something like that in code would look like this, though I will not read it out loud. Okay, so maybe that's how you implement depth first paths. And again, we wrote it as a separate class represented by this little bodhisattva in the corner, but you could also write this as part of your graph class if you so choose. So maybe your graph class provides a service to the users, which is depth first search, but that's up to you. Okay, at long last, we talked about the services a graph can provide. We took a little detour and reminded ourselves of what depth first paths is and how that might look in code depending on what services we give to our users. Now we can finally answer the question that we were all curious about. I guess maybe you weren't, but I was curious about, which is, how do you actually represent the graph in memory? What data structure do you use to represent the graph? Like, I was drawing these little pictures on the slide, but how do you write data structures? Like, do you use a list? Do you use an array? Do you use something else? How do you represent the graph? And our decisions are going to affect how fast it is to perform operations on this graph. So do you remember with trees, there were all these different representations, and they all represented the same picture. So like, here's my little picture of a tree, and I could represent the tree using links that are recursive. I could use that array that we saw from, I don't know, 2 or 3 lectures ago. So we could do this instead. And so there were all sorts of different ways to represent the same tree. Well, let's take the same idea and apply it to graphs. So just like how there were all these different fancy ways to represent trees in memory, there are all sorts of different data structures you can choose to represent graphs for the user. The user wants to see this picture. How do we as the monks make it happen? We have lots of different choices. So I will show you 2. Okay, and you can invent others if you like. So the first one I'm going to propose is called the adjacency matrix. Ooh. So this one is actually pretty simple. I'm going to create a 2D table, 2-dimensional table. And in the table, I'm going to write down whether an edge exists between the 2 vertices or whether it does not. So for example, is there an edge between 0 and 3? I look at the picture, no. So in my adjacency matrix, what is this? Row 0, column 3, I write a 0 to indicate there is no edge between those 2 vertices. And likewise, row 3, column 0 is a 0 to represent that there is no edge between those 2 vertices. But look at 1 and 2. There is an edge between them. So I go to row 1, column 2, I write a 1 to represent the fact that there is an edge between those 2. And likewise, because this is an undirected graph, then I will also say there's an edge from 2 to 1. So I'll go row 2, column 1, I'll mark it as 1. So if it's undirected, I would have to put 2 1s, one representing the 1 to 2 edge, another one representing the 2 to 1 edge. That's my decision. Again, if you want to invent something else, go nuts, but that's what I chose to do. If the graph is directed, then maybe you don't have the symmetry. So instead here, there is an edge between 0 and 1. So I go to row 0, column 1. I write down the 1 to represent an edge between 0 and 1. But because this graph is directed, there is no edge from 1 to 0. So I go to row 1, column 0. It's a 0. It represents no edge between 1 and 0. So in this case, the matrix is not symmetric. But How you implement it is up to you. It's just some 2D array, and in the array, you write down zeros when there's no edge, and you write down ones when there's an edge. That's it. Relatively simple. Okay. So that's one possible decision you could make, one way you could represent a graph, because you can't draw this picture in memory, but you could build this 2D array. Okay, there's a second representation. I have never seen anyone use this, so I'm just not going to talk about it. But if you're curious, you could represent a set of edges. But again, I've never seen anyone do it, so enough said about you. Okay, next. Okay, here's another representation. This one is very common, it's very popular. I recommend it. So I guess I will start by saying, why might this adjacency matrix representation be not super useful? Well, imagine you have a gigantic graph, like 1,000 nodes. So maybe the nodes represent, I don't know, the people in this class, 1,000 nodes. And maybe the edges represent people who are friends in the class. Well, if you think about this graph, is this graph extremely connected, or is it pretty sparse? So that is it the case that everybody is friends with every other person in the class, and there are tons of edges and tons of ones in this adjacency matrix? Or is it more likely that everyone is friends with like one or two other people, but probably not everyone, so most of this big matrix is just lots of zeros? So unless you were all like social butterflies and you're friends with like 900 other people, and I don't know about it, I think it's more likely that everyone's friends with a couple people, but not 100 or 900 people. And so the graph is going to be pretty sparse. So there will not be too many edges in the graph compared to the maximum number of edges that could exist. Most of the edges don't exist, so your adjacency matrix will just be tons and tons and tons of zeros and just a few little ones scattered around. And so while that works, it's a little inefficient to store all the zeros. So here's the alternate approach that helps for sparse graphs, which is I'm going to keep an array of lists. So list here, another list, another list, another list. So it's an array of lists, and each list tells me a list of who is adjacent to that vertex. Maybe I phrased that weird. Here's an example. So index 0. Well, what is 0 adjacent to? I look in the graph. It's adjacent to 1 and 2. So my list has 1 and 2. Vertex 1. Who is it adjacent to? It is adjacent to vertex 2. So I have a list of just the number 2. And vertex 2, you are adjacent to nobody. So you have an empty list corresponding to index 2 in the array of lists. So it's just a bunch of lists. The ith list tells me all the vertices that are adjacent to vertex I. Okay, that's the adjacency list. I like it because now I don't have to store all the zeros, and it's nice because a lot of real-world graphs, like the graph of friends or whatever, is pretty sparse, and most entries in the adjacency matrix would be zeros, unless you all have 999 friends, and I don't know. Okay, so there were 2 choices, plus one really weird one that no one talks about. And so those are your choices for how to implement the graph. So we decided what the services are to give to the users, and then separately, we made another choice, which is how do you represent the graph in memory? Adjacency list, adjacency matrix, the weird one that no one talks about, it's your choice. Okay, now let's do some runtime analysis. I will warn you ahead of time, it's a little gross, so I'm sorry. But let's think about the runtime of, well, let's think of the runtime of this print method. So remember this print method, it said, I'm going to go through all the vertices, and then for every vertex, I'm going to look at all the adjacent vertices, and then print out how many, or print out every single edge in the graph. And so the question for you is, how long does this take if I choose to use an adjacency list representation? So I want to use this list representation where every single vertex has a list telling me all the adjacent vertices. And I want you to tell me between these 4 choices, what is the order of growth of the print method relative to the size of the graph? As the graph grows large, how fast does this thing take? If I have a graph with V as the total number of vertices and E as the total number of edges. And remember, E is the total number of edges. So in this graph, E is 3 because there are 1, 2, 3 edges in total. Okay, so I'm not gonna lie, it's kind of annoying. And the main thing that makes this annoying, if you stare at it, is you're like, wait a minute, there are 2 variables. I thought 1 variable was hard. Now there's 2. What the heck? So By the way, people on Zoom can still hear me? There's no complaints? Because the battery's almost dead. Okay, let me know. Okay, let me know. So the annoying thing is you were like, I thought asymptotics with one variable was hard enough. Now you're giving me two. What the hell? So the reason why we need two variables is because when I say a graph grows large, I have to be more specific because there are actually multiple ways in which a graph can grow big. So if you think about it, like a list, how does a list get big? I add more things to it, and that's it. But how does a graph grow big? It turns out there are multiple ways in which a graph can grow big. One possible way for my graph to get bigger is I have more vertices. So it's like there are more people in the class. So there are 1,000 people, there are 2,000 people, there are 3,000 people. So the graph could get bigger if there are more vertices. That's one way for the graph to get big. But there's another way for the graph to get big, which is what if the class size stays the same, so still 1,000 people, but you all start suddenly making lots and lots of friends. In that case, the graph number of vertices stays the same, but the total number of edges increases because you're all making friends with each other, and so the number of edges increases. So it turns out to really think about this graph, I need to think about two ways in which the graph could get big. Your graph could get big if there's a lot of vertices or if there's a lot of edges. There are two different independent ways in which the graph could grow, and we have to consider both of them. That's what makes this problem hard. Okay, having said that, let's start thinking about this. So how long does it take to iterate over these neighbors? So let's think about this inner for loop. How long does it take to go through one of these lists? Well, I don't know how long the list is. This list could be empty. That means that you have no friends. So kind of depressing, but the list would be empty. Or maybe you're friends with everybody. Then this list would be huge. In fact, it would have the items because you're friends with all the other people in the class. So the runtime here, it could be, in the best case, omega of 1. That means it's at least omega of 1. That would be the case in which you have no friends and this list is empty. This could also be big O of v in the case where you're friends with everybody and this list is totally full, has all other vertices in each of these lists. And how many vertices do we have to consider? We have to iterate through this first one and the second one and the third one. V vertices in total, that's this outer for loop. So in the best case, I have theta of v. That would be the case in which there are lots of vertices, but nobody has made any friends. There are no edges. So I would just go through first one, empty. Second one, empty. Third one, empty, empty, empty. And I would just go through v vertices, find out that all of them are empty, and print out nothing. That would be a very depressing graph, but it would be a theta of v runtime. By contrast, the graph that is fully connected, every single edge that could possibly be there is there, that would be the graph in which I go to 0, I look at the list, it's totally full, v things, and I have to print them all out. Then I go to 1, how many things? V things, I print them all out. I go to 2, how many things in this list? V things, I print them all out. So there are v vertices in total. If for each one I have to print v things, I would get a runtime of v squared in the worst case. So in the best case, theta of v. In the worst case, where everything is connected, theta of v squared. Okay, problem. I didn't give you that. That's not one of the choices. So which of these choices best represents the runtime, not just in terms of v, which was our first attempt at analysis, where we just use v to think about best case, worst case, but how would you answer this if I wanted you to answer in terms of v and e? Because remember, the graph can grow big in two ways. There could be lots of people, or there could be lots of edges. That is, you could all be friends. So how do you answer this? It's kind of weird, and it's kind of gross, I'm not going to lie. So here's how I think about it, and I will admit it's kind of annoying. So how many vertices do you have to consider? You have to consider the vertices, no matter what. That is, you need to look in this box, this box, this box, this box. So in total, you need to look at the memory boxes to find all the lists. That is always true. Whether these lists are empty or full, you got to look at v boxes. There's no way around it. Also, for each box, you need to consider this list. And well, I don't know how many things are in this first list. I also don't know how many things are in the second list. I also don't know how many things are in the third list. I know it's between 0 and v, but I don't know how many things are in each of these lists. But can you tell me how many total things are in all of the lists together. So if I take the number of things in this first list and the number of things in this second list and the next list and the next list, and I take them all and I add them up, how many things are in all of the lists bundled together? E, right? Okay, so that was kind of awkward. E things in the list because there's one item per edge. So if I take all the lists and I combine them together, there should be E total things in all of the lists. So I need to look at V memory boxes. And separately, I need to look through all these lists. And there are E things in the list in total. So I think the answer is V plus E. Another way of saying it is how many memory boxes do I look at? V of them. And how many items do I print? I print E, or if my graph is undirected, then I guess I print 2E things. So in total, I have theta of V plus E. And again, I know it's kind of gross, but that's what happens when I have two variables. Question? Why is it not V times E? That's a good question. So maybe I'll phrase it another way and see if you like it better. So another way I think about this is, well, there's two ways in which this graph could grow big. One way in which this graph could grow big is there are tons and tons of vertices, like 1,000 vertices, 10,000 vertices, 1,000,000 vertices. That'd be a very big class. But nobody is making friends, so there are no edges. In that case, which of these two terms dominates? Well, there's no edges, so this E term is really small, but this V term starts to dominate. And so if I create tons and tons of vertices, then the thing that is slowest is looking at all these memory boxes. So V dominates, and so this reduces to theta of V, because V is the fastest growing term. By contrast, what if V stays small? Like it's a pretty small class, 1,000 people, but everyone starts to make friends and like there are tons and tons of edges. Well, in that case, E starts to dominate, and the V term becomes pretty small in comparison to E. So in that case, looking through these memory boxes is not that slow compared to the fact that all of these lists are gigantic, and I have to look through E edges in total, where E is very large. So another way of thinking about this sum is that it allows me to say if V is the one that's growing larger, then V dominates and it's theta of V. By contrast, if E is the thing that is growing largest, then E dominates and becomes the largest thing. So maybe that's another way to think about it. I don't know if it totally helps. I will admit it's kind of gross. Do you have a 10-second explanation for why V times E is the wrong answer here? Each edge is only connected to two vertices.
It's impossible for every single edge to be connected to all V vertices. So each edge only contributes at most twice within the for loop.
Yeah, that's another good way of putting it. So each edge only contributes at most twice. So if it's an undirected graph, the edge appears twice. So V times E would be saying for every edge, repeat it V times. But if I look at this code, there is no place where I'm trying to repeat an edge V times. Every edge gets printed twice or once. So V plus E is the better answer. But again, I'll admit, this is one of the more disgusting things I have to show you. I had to stare at this like for a couple minutes to really wrap my head around it. So maybe a good one to look at after lecture. OK. But in the interest of getting through everything, oh, here's another slide with a lot of words if you want to read it in words. But V plus E. Sorry, it's kind of gross. I apologize. OK. Again, you could think of it as max V and E, which is what I said earlier. But I will say it's kind of gross, so I'm sorry. A double sorry. Triple sorry. OK. So here's depth first paths again. We saw this earlier. And so we could also think about the runtime of depth first paths, which is how fast is it to run this code and go through the entire graph? I'm not even going to make you think about it because it's kind of gross. It turns out the answer is the same. It is also V plus E for mostly the same reasons that we talked about before, which is how many vertices do you have to mark? You need to mark V vertices because you have to go to every vertex in the worst case and mark it. How many edges do you have to consider? That is, how many edges do you have to look at and like write down that potential edge to or check that it's marked and don't visit it again? Well, you need to consider E edges. And again, each of these could make the graph big. So we write V plus E to remind ourselves the graph could grow big if there are tons of vertices but no edges. Then all of my time is just spent marking all the vertices, and then V would dominate. Or maybe there's not a lot of vertices and there's tons of edges. In that case, E would dominate, and all of my time would be spent looking at all the edges that come out of every vertex. So that's the runtime for depth-first paths. Again, it's kind of unsavory. You might have to stare at it a little bit. Sorry. OK. I will not even answer this because I think it's kind of too confusing for lecture, but you can read it if you're interested. OK. So that's the runtime of depth-first paths. We will fill this with more algorithms, I guess, now, unless you have other questions. But I want to show you one more algorithm. I think it's cool, so we will look at it. OK. Do you remember this slide from last time, aka from 10 minutes ago? OK, good. So remember how we said there are many different orders in which you could traverse or iterate through a graph. For example, I showed you DFS preorder, which is you run DFS and you do something before the recursive DFS calls, you get this order. This would be the order in which DFS methods are called. You could also do something after the DFS methods on the neighbors are called. That would be equivalent to this order, or the order in which the DFS calls return, and you get this order. But do you remember when we talked about trees? We talked about inner order, post order, but there was one more order that I talked about very briefly, and now I'm going to show you the graph equivalent. So remember in the tree, there was this level order where I said, let's go top to bottom, left to right, D, B, F, A, C, E, G. Do you remember that order? Turns out that order also has a graph equivalent. So the graph equivalent of that level order of the tree, which is to go just layer by layer, top to bottom, that exists, and it's called breadth first search. So we're going to try to do that level order thing from the tree, but we're going to do it on the graph. So in the tree, I can think about it as I'm going to look for all the things 0 away from the root. That's the root. That's D. Then I'll look at all the things 1 away from the root. That's B and F. Then I'll look at all the things 2 away from the root. That's A, C, E, G. So I could do the same thing in the graph. What are all the things 0 away from the source, which is S? Well, that's 0. What are all the things 1 away from the source? That's 1. What are all the things 2 away from the source? Well, there's 4. It's 2 away from the source. And there's 2. It's 2 away from the source. What are all the things 3 away from the source? Well, 1, 2, 3. That's 3 away from the source. 1, 2, 3. That's also 3 away from the source. So you can almost think about it like these are all the things 0 away. That's 1 away. That's 2 away. Those are 3 away. And then eventually, toward the end, I get to all these very far away nodes. So I start with all the closer nodes, and then I iterate my way to all the further nodes. That's BFS. We want to find an algorithm in pictures and then later in code for doing that. OK, so if you're watching the video, you could pause me and try to figure it out. But since we're in person and I want you all to go home on time, I will just spoil it. But remember, I want to keep track of this order. I want to keep track of all these closer things first and then visit the further things later. OK, so here's the key idea. And it's kind of weird. The key idea is, you know I'm a big fan of recursion, but I do not want you to use recursion for this one time. And so here's the idea, which is we're going to use a queue. And what's a queue? Well, it's a data structure where you can add to the front, or sorry, you can add to the back, and you can remove things from the front. So it's like if you go to the grocery store. There's a lot of store things today. You go to the grocery store or whatever, and you get in line in the back, and then people leave the line in the front. Or I guess if you're British, you call it a queue. OK, so that's the queue. It's a data structure. You can add things to the back, and you can remove things from the front. So it's like a line at the store. So here's what we will do. We will pluck, or we will remove vertices from the front of the queue. So when everyone gets in line, we take the people who make their way to the front of the line. And then for everyone who's unmarked, just like depth first search, I mark anyone who's unmarked. I write down how to get there using the H2 array. And then I add the new vertex to the end of the queue. So they get in line behind me. And this queue, this data structure, this is what's going to guarantee that I visit closer nodes before further nodes, because I have a line. So all the nodes that are far away are going to get in the back of the line. I'm going to be like, you're far away. You need to go to the back of the line and wait your turn. And I'm going to process all the nodes that are close before I get to all the nodes that are far. That's what the queue is going to guarantee. That's what makes breadth first search work. So even if you don't look at the slide in the demo that I'm about to show you, The key idea is I have a queue, and the queue basically says, if you're far away, you need to get in the back of the line and wait your turn because I'm going to process all the closer things first. Okay, with all that said, let's watch it in action. So here's my queue. It is a very lonely queue because there's nobody inside. But I'm going to start by putting the starting vertex in the queue. So look, it got in line. Okay, great. And I marked it because I don't want to visit vertices twice, just like before. Okay, so let's go to the line. We're the little cashier in the grocery store. We're going to take someone from the front of the queue. Well, who's in line? 0. So it's your turn. Well, we're going to pull you off the queue, and we're going to consider all of your neighbors. Who are your neighbors? Well, you've just got one neighbor, and it's 1. And so we'll throw you in the queue. So 1, get in line and wait your turn. So look, it's in the queue. And we'll also write down how to get to 1, just like we did from last time. So we'll use edge2 to remind ourselves how to get to 1. If you want to, you can also keep track of the distance to each of these nodes, although in the interest of me talking, I will not talk about it, but you can also do this if you want. Okay, so 1's in line. So I finished processing 0. What's next? I need to go to the queue and take the next person. So who's the next person in line? Well, it's 1. Okay, great. So I take 1, I mark it, and I consider all of its neighbors. Who are its neighbors? 4 and 2. So 4 and 2, get in line and wait your turn. So there they are. Okay, here comes the interesting part. So I'm going to go to the queue, take the next person in line. Who is it? It's 2. So I take 2. Okay, great. I mark it, and I consider all of its neighbors. Now look at this neighbor right here, 5. Is 5 close to 0? I think it's pretty far from 0. So here's the key idea. This is the moment that you'll see breadth first search work its magic. I'm going to put 5 on the queue, but where am I going to put it? Ready for this? Look at 5. It's in the back of the queue. I'm going to tell 5, wait your turn. You are far away. I want to process the closer things like 2 and 4. So 5, you got to get in the back of the line and wait your turn. I need to finish processing 2 and 4 because they were closer. That's the key idea. So look, 2 and 4 are in the queue, and when I put 5 in the queue, it goes in the back because it's got to wait its turn. I do not want to process 5 until I'm done taking care of 2 and 4 because those were closer. So let's finish taking care of 4. So I take 4 off the queue. I look for its unmarked neighbors, which is 3, and I put 3 on the queue. And look, again, so 3, get in line. You need to wait your turn. Okay, so now 5 and 3 are in the queue. I take 5, and again, 5 has 2 neighbors, 6 and 8. And look, they need to wait their turn. That's the key idea. That's the invariant that makes this work. So the invariant that makes this work is that everybody who gets queued, they need to go to the back and wait their turn because I got to process all the closer nodes first. So I process 3. Okay, great. 3 has no neighbors, so no one goes in the queue. Everyone's marked, so no one goes in the queue. Okay, who's next? 6. I take 6 off the queue. I add 7 to the back. I process 8. There's no neighbor, so I don't add anybody to the queue. I process 7. There's no one to add. The queue is empty. Everyone is marked, and we're done. Okay, one final thing I will say about the invariants before you all go. Right here, I will admit this invariant is a little bit hard to see with the graph so small, but I encourage you to go home and think about it. The invariant that really makes breadth first search work, I kind of said it very generally when I said nodes that are far away, they get thrown to the back of the queue so they can wait their turn. Another way of saying that more formally is that when you're on the queue, you are either distance k or k plus 1 away from the source. So for example, let's say I have a queue, and it's got all the people who are 3 away from the source. So what am I going to do? I'm going to take someone who's 3 away from the source. I'm going to pluck them off the queue. I'm going to throw all of their neighbors. And if you're 3 away, then all of your neighbors are 4 away. So a bunch of people with distance 4 are going to get thrown on the queue, and they have to wait their turn because I need to process someone else who's 3 away. So I take the next person who's distance 3. I consider all of its neighbors, and how far are all of its neighbors? 4. So they all go to the end of the queue, and I process someone else who's distance 3. I throw a bunch of people who are distance 4 on the queue. So at any given time, when I'm running BFS, I have tons of people who are distance 3. I take them off the queue one by one. As I take them off the queue, I put all of their neighbors who are distance 4 in the back of the line. And only after I finish processing all the people who are 3 away, then who's next up? The person who's 4 away. So now it's your turn. I take the person who's 4 away, and I take all of its neighbors who are 5 away, and I put them on the fringe. And so now I'm processing people who are distance 4, and I'm throwing a bunch of people who are distance 5 on the fringe. That is what this invariant says in some more words. So at any given time, you have a bunch of people who are distance, say, 4. I'm processing them, and as I process all the people distance 4, I throw a bunch of nodes that are distance 5. Once I finish all the people who are distance 4, now it's time to process all the people who are distance 5. And as I do that, I go and I throw a bunch of people with distance 6 at the end of the queue. So that's the idea. And again, although I didn't talk about it in great detail, as I visit every node, I can write down the edge to, which tells me how I got to that node. And that's how I represent all the paths. And if I wanted to, I could also keep track of the distance to every node. So I could write down how far it was to get to that particular node. I will not even read this because of time. But if you're interested, you can check this out. It's just pseudocode for what I just said in words. I will not even talk about the runtime. But it's kind of the same thing as what we saw before, which is there are v vertices to consider. That is, there are v vertices that are going to come off the fringe, which is a list of vertices that get in line. And there are e edges that I have to consider and mark. OK, so I guess that's it for today. Remember, my favorite picture are decisions for how to implement graphs. Do I use this? Do I use this? Will have a huge effect on the runtime for our users. OK, that's it. See you next time. Oh, I didn't get to this slide. OK. Well, that's OK. I think you can figure out this slide on your own for the folks on the recording if you wanted to. OK. Goodbye.